My name is René Fabricius. In this video, I will briefly summarize our paper Bridging Performance Gap between Minimal and Maximal Support Vector Machine Models, published in the journal Transactions on Machine Learning Research. Support vector machine is a popular and efficient binary classifier. Its application scope is broadened by several multi-class extensions, most of which rely on combining multiple binary SVMs. Computational complexity of these extensions is at least quadratic in the number of classes. This is making it impractical to use for problems with hundreds or thousands of classes. Would it be possible to modify one of these extensions in a way that would allow its use on large datasets such as ImageNet? That is the question we are trying to answer in this paper. Multi-class extension which we are working on is called 1 versus 1. It consists of training a binary SVM for each pair of classes. Each SVM is trained on a subset of the training set belonging to the two relevant classes. At prediction time, all the samples are fed into all the binary SVMs. Each binary SVM produces a binary classification. All these binary classifications are combined by a pairwise coupling method, which in turn produces final multi-class prediction. 1 versus 1 approach by default contains a binary SVM for each pair of classes. We call such a model maximal. Set of binary SVMs employed by a multi-class approach can be represented as a graph where nodes are classes and edges are binary SVMs distinguishing between the two classes corresponding to the nodes that they are connecting. On the image is displayed a maximal model with 5 classes. However, it is possible to build a multi-class SVM from just C-1 independent binary SVMs, where C is the number of classes. Such models we call minimal. In contrast to a single maximal model, there are multiple minimal models. Each is corresponding to a spanning tree on a graph, where nodes correspond to classes and edges to binary SVMs. There are 3 examples of spanning trees displayed at the bottom. We have examined several minimal models and found the star graph displayed on the left to be the best concerning the output accuracy. Therefore, we use it as a starting model for building intermediate models. Intermediate models contain more binary SVMs than minimal models, but fewer than maximal model. They can be created from minimal models in incremental steps by adding a single or several binary SVMs. By this process, we ultimately get the maximal model. In our paper, we examine and compare several strategies for choosing the edge to add. In the bottom, there is an example of incrementally adding 1, 2, and 3 edges to a minimal star model. In this plot is displayed the evaluation of our most successful strategy for choosing which edge to add. Evaluation is performed on a dataset ImageNet 50, consisting of a subset of 50 ImageNet classes. Two popular SVM kernels are used, linear and radial. These correspond to plot columns. On the vertical axis, there is accuracy of the model, and on the horizontal axis, there is the number of edges, or binary SVMs, in the model. Leftmost point on each of the plots corresponds to a starting minimal model, and the rightmost point to the maximal model. Intermediate models between them are created by iteratively applying our approach and adding a binary SVMs to previous model. In both plots, we can see that most of the accuracy gains are realized by adding just 20 to 30% of the edges contained in the maximal model. This provides considerable performance improvements. Another thing that we can observe is that when using radial kernel, even minimal model has a relatively very high accuracy. All the details about our multi-class SVM approach and about performed experiments can be found in our paper and in our public GitHub repository. Thank you for your attention. An implementation pro tip. For large problems, it's very beneficial to use GPU implementation of binary SVM in RapidsQML. It's really fast.